Bismillahirrahmanirrahim. Assalamu alaikum. My name is Javeria Zafar. Today I am going to present about subatomic particles. First of all, we should know what is subatomic particles. I hope you all know about atoms. Actually, subatomic particles are smaller than an atom. According to the standard model of particle physics, a subatomic particles can be either a composite particle which is composed of other particles, for example, proton, neutron, meson, or many others. And second one is elementary particle, which is not composed of other particles, for example, an electron, photon, or muon. Particle physics and nuclear physics study these particles and how they interact. Let's discuss some subatomic particles one by one. Number one is quark. Quark is a type of elementary particles, means it is not made from any other subatomic particles. Any member of a group of elementary subatomic particles that interact by means of the strong force and are believed to be among the fundamental constituents of matter. Quarks appear to be true elementary particles. That is, they have no apparent structure and cannot be resolved into something smaller. Quarks combine to form composite particles called hadrons, which is the most stable of which are protons and neutrons. All commonly observable matter is composed of up quarks, down quarks, and electrons. They can be found only within hadrons, which includes baryons and mesons. Quarks have many intrinsic properties, which includes electric charge, mass, color charge, and spin. Quarks are the only elementary particles in the standard model of particle physics to experience all four fundamental interactions, which is also known as fundamental forces, that includes electromagnetism, gravitation, strong interaction, and weak interaction, as well as the only known particle whose electric charges are not integer multiples of the elementary charge. Quarks have six different types, which is also known as flavors of quarks. These include up quarks, down quarks, charm quarks, strange quarks, top quarks, and bottom quarks. Up and down quarks have the lowest masses from all quarks. The heavier quarks rapidly change into up and down quarks through a process of particle decay, the transformation of higher mass into the lower mass state. Because of this, up and down quarks are generally stable because they will not decompose into the smaller particles and the most common in the universe. While strange, charm, bottom, and top quarks can only be produced in high energy collisions. For every quark flavor, there is a corresponding type of antiparticle which is known as antiquark that differs from the quark only in that some of its properties having electric charge, but they have equal magnitude but opposite sign. Next subatomic particle is mesons. Mesons are the hadronic subatomic particles. They composed of an equal number of quarks and antiquarks, usually one of each bound together by strong interactions. They have a meaningful physical size, a diameter of round about 1 femtometer, which is about 0.6 times the size of our proton and neutron. All mesons are unstable, with the longest lived lasting for only a few hundreds of a microseconds. Heavier mesons can decay into the lighter mesons and ultimately to stable electrons, neutrinos, and photons. Mesons formed during the high energy collisions between particles made of quarks. It's mean when those particles which are made from quarks are collide with one another, then these particles mesons are produced, such as cosmic rays and baryonic matter. Baryonic matter actually contain odd number of valence quark and belong to the Hedron family. Mesons are routinely produced artificially in cyclotrons or other accelerators in the collision of protons, antiprotons, and other particles. Cyclotrons is the type of particle accelerator also. Next is pions. A pion or a pi meson denoted with the Greek letter pi. Pi is any of three subatomic particles pi 0, pi plus, and pi minus. Each pion consists of a quark and an antiquark and is therefore a meson. Pions are the lightest mesons and more generally the lightest hadrons. You can say pion is actually the first meson which is to be discovered. They are unstable with the charged pions pi plus and pi minus decaying after a mean lifetime of 26.033 nanoseconds, and the neutral pion pi 0 decaying after a much shorter lifetime of 85 attoseconds. They are very unstable because they live for a very small time. Charged pions most often decay into muons and muon neutrinos, while neutral pions generally decay into gamma rays. Commonly, pions produced during the collisions of hadrons. High energy collision between hadrons produce the pion subatomic particles. Pions also produce in natural processes when high energy cosmic ray photons and some hadronic cosmic ray components interact with matter in Earth's atmosphere. Pions are used in medical radiation therapy for the treatment of cancer. Lepton. Lepton is an elementary particle of half integer spin 1 by 2, that does not undergo strong interaction. Lepton have two main classes which exist: charged leptons, which we also known as electron-like leptons and muons, and the second one is neutral leptons. They are also known as neutrinos. Charged leptons can combine with other particles to form various composite particles such as atoms and positronium, while neutrinos rarely interact with anything and are consequently rarely observed. The best known of all lepton is the electron. From electron, we all know its properties. Electrons have the least mass of all the charged leptons. Muons and taus will rapidly change into electron and neutrinos through a process of particle decay transformation from a higher mass state to a lower mass state. The electrons are stable and the most common charged lepton in the universe, while muons and taus can be produced only in high energy collisions. Here is some types of leptons. Leptons have 6 types, which is also known as flavors. They grouped into 3 generations. The first generation of leptons is called electronic leptons, comprises the electron and the electron neutrino. And the second one are the muonic leptons, comprising the muon and the muon neutrino. And the third generation of leptons is the taionic leptons, comprises the tau and the tau neutrino. I have tell you about their intro. For every lepton flavor, there is a corresponding type of antiparticle which is known as antilepton. 3 fundamental interactions between them is present, which are gravitation, weak interaction, and the electromagnetism. Next one is muon. The muon, which is from the Greek letter mu, is an elementary particle similar to the electron, with an electric charge of -1 e and a spin of 1 by 2, but with much greater mass. Muon have very high mass. Firstly, it is called a meson, but later it is considered as a classification of leptons. As like other leptons, Muon is not having any substructure, means it is not composed of any simpler particles. Muon is an unstable subatomic particles much longer than many other subatomic particles. Unstable subatomic particles with a mean lifetime of 2.2 microsecond. Muons are not produced by radioactive decay because it has a greater mass and energy than decay energy. Muon decay almost always produces at least three particles, which must include an electron of the same energy as the muon and two types of neutrinos. Muon has a corresponding antiparticle of opposite charge plus 1e, but equal mass and spin. This is called anti-muon. Muon has a mass of 105.66 mega electron volt, which is approximately 207 times than that of the electron, which is very large. Due to their greater mass, muons accelerate more slowly than electrons in electromagnetic fields, emit less deceleration radiation. This allows muons of a given energy to penetrate far deeper into matter. Because the deceleration of electrons and muon is primarily due to the energy lost by the deceleration mechanism. As with the other charged lepton, the muon has an associated muon neutrino, which differs from the electron neutrino and participate in different nuclear reactions. Next particle is Kaon. A kaon, also called a K-meson. It is also the classification of meson and denoted with K is any of a group of four mesons distinguished by a quantum number called strangeness. Strangeness is a property of particle expressed as a quantum number for describing decay of particles in strong and electromagnetic interactions, which occur in a very short period of time. Kaon is actually the first strange particle. In the quark model, they are understood to be bound states of a strange quark and an up or down quark. Quark model is a classification scheme for hadrons in terms of their valence quark, the quarks and antiquarks which give rise to the quantum numbers of the hadrons. Kaon discovered in cosmic rays, and it is found to be a good source of information on the nature of fundamental interactions. Next one is baryon. A baryon is a type of composite subatomic particle which contains an odd number of valence quarks, which is at least 3. Baryons belong to the Hedron family of the particles and Hedron family which is composed from quarks. Baryons are also classified as fermions because they have half integer spin. The name baryon, introduced by Abraham Pace, comes from the Greek word for heavy because at the time of their naming, most known elementary particles had lower masses than the baryons. Each baryon has a corresponding antiparticle where their corresponding antiparticle replace quarks. The most familiar baryons are protons and neutrons. Protons, which is made from two up quarks and one down quarks. Actually, protons and neutrons, they both of which contain three quarks, and for this reason, they are sometimes called triquarks. These particles make up most of the mass of the visible matter in the universe and compose the nucleus of every atom. Exotic baryons containing 5 quarks. Exotic baryons are actually the type of hadron with half integer spin but have a quark content different from the 3 quarks present in conventional baryons. They are called pentaquarks. Pentaquarks are the man-made subatomic particles consisting of 4 quarks and 1 antiquark bound together. They are not known to occur naturally or exist outside of the experiment specifically carried out to create them. They both have been discovered and studied. Next is gluon. Gluon is an elementary particle that acts as the exchange particle for the strong force between quarks. It is analogous to the exchange of photons in the electromagnetic force between two charged particles. Gluons bind quarks together, forming hadrons such as protons and neutrons. You know, protons and neutrons have three quarks, which are actually bind from the gluons. Gluons are vector gauge bosons that mediate strong interactions of quarks in quantum chromodynamics. The confusing term in this point is vector gauge bosons. Actually, it is a vector boson. Vector boson is a boson whose spin is equal to 1. They are regarded as elementary particles in the standard model. That's why they are called gauge bosons. And the quantum chromodynamics is the theory of strong interaction between quarks mediated by gluons. Gluons themselves carry the color change of the strong interaction. This is unlike the photon, which actually mediates the electromagnetic interaction but lacks an electric charge. Gluons therefore participate in the strong interaction in addition to mediating it, making QCD significantly harder to analyze than quantum electrodynamics. Quantum electrodynamics describes mm, how light and matter interacts with one another. Next one is photon. Photon concept originated during the first 2 decades of 20th century with the work of Albert Einstein, who built upon the research of Max Planck while trying to explain how matter and electromagnetic radiation could be in thermal equilibrium with one another. Planck proposed that the energy stored within a material object should be regarded as composed of an integer number of discrete equal side parts to explain the photoelectric effect. Einstein introduced the idea that light itself is made of discrete units of energy, and he used the term photon for these energy units. From this history, photon words arises. The photon, which means light, is a type of elementary particle. It is the quantum of the electromagnetic field and including electromagnetic radiation such as light and radio waves, and the force carrier for the electromagnetic forces. Photons are massless particles and has no electric charge, so they always move at the speed of light in vacuum. The photon belongs from the class of bosons. They have two types of nature, which is called wave particle duality, because they behave like wave as well as particle. Photons and some other elementary particles are described as a necessary consequence of physical laws having a certain symmetry at every point in space-time. The photon concept has led to momentous advances in experimental and theoretical physics, including lasers, Bose-Einstein condensation, quantum field theory, and the probabilistic interpretation of quantum mechanics. It has been applied to photochemistry, high resolution microscopy, and measurements of molecular distances. And photons have been studied as elementary elements of quantum computers and for the applications in optical imaging and optical communication, such as quantum cryptography. Next one is bosons. A boson is a subatomic particle whose spin quantum number has an integer value 0, 1, 2 up to so on till infinite. Bosons form one of the two fundamental classes of subatomic particles, the other being fermions, which have half integer spin. Every observed subatomic particle is either a boson or a fermion. Some bosons are elementary particles and occupy a special role in particle physics, unlike that of fermions, which are sometimes described as the constituents of ordinary matter. Some elementary bosons, for example, gluons, which acts as a force carriers, which give rise to forces between other particles, while one give rise to the phenomena of mass. Other bosons, such as mesons, are composite particles made up of smaller constituents. There are 5 elementary bosons. One is scalar boson having spin 0 and the second one is vector boson. These terms are already explained in this lecture. Having vector bosons are dot having spin 1 that acts as a force carriers. Composite particles such as hadrons, nuclei and atoms can be bosons or fermions depending on their constituent. Since bosons have integral spin, and fermions or half integral spin, any composite particle made up of an even number of fermions is a boson. Fermion. The word fermion not to be confused with fermium. Fermium is a synthetic element with a symbol of capital F with small m having atomic number 100. A fermion is a particle that follows Fermi direct statistics and generally has half odd integer spins, spin 1 by 2, spin 3 by 2. These particles obey the Pauli exclusion principle. Pauli exclusion principle is the quantum mechanical principle which states that two or more identical fermions can't occupy the same quantum state within a quantum state simultaneously. Fermions include all quarks and leptons as well as all composite particles made from the odd number of these, for example, baryons and many atoms and nuclei. Fermions differ from bosons which obey Bose-Einstein statistics. Some fermions are elementary particles such as electrons and some are composite particles such as protons. According to the spin statistics theorem in relativistic quantum field theory, particles with integer spins are bosons. Integer spins number that can be written without a fractional component, while particles with half integer spins are fermions. Half integer spins that number which is written with fractional component. Fermions are Fermions are usually associated with matter, while bosons are generally force carrier particles. Although in the current state of particle physics, the distinction between two concepts, fermions and bosons, are unclear. Weakly interacting fermions can also display bosonic behavior under extreme conditions. At low temperature, fermions show superfluidity. Superfluidity, you can say it is a property of a fluid with zero viscosity, means flow without any loss of kinetic energy for uncharged particles, and superconductivity for charged particles. Superconductivity in which electrical resistance vanishes and magnetic flux fields are expelled from the material. So charged particles show superconductivity and the uncharged particles show superfluidity. I hope these both terms are clear to you. Composite fermions such as protons and neutrons are the key building blocks of everyday matter. The Standard Model recognized two types of elementary fermions, quarks and leptons. In all, the model distinguished 24 different fermions. We know there are 6 quarks, up, down, strain, charm, bottom, and top, and 6 leptons: electron neutrino, muon neutrino, and ton neutrino, along with the corresponding antiparticle of each of these. I will not explain this point briefly because I have already explained about them. Mathematically, fermions come into 3 different types, which are classified as Weyl fermions, in which particles are massless, direct fermions, which are massive, and Majorana fermions, each its own antiparticle. Next subatomic particle is anion. An anion is a type of quasi-particle. I have mentioned the quasi-particle description in the next slides, where I will tell you about the kind of particles. Here a little intro I will give you that quasi-particles are like collective excitation. They both are closely related emergent phenomena arising when a microscopically complicated system, such as you can say a solid, behaves as if it contained different weakly interacting particles in vacuum. that occurs only in two-dimensional system with properties much less restricted than the two kinds of standard elementary particles, fermions and bosons. In general, the operation of exchanging two identical particles, although it may cause a global phase shift, can't affect observables. Anions are generally classified as abelian or non-abelian. Abelian anions Abelian anions detected by two experiments in 2020 play a major role in the fractional quantum Hall effect, and the non-abelian anions have not been definitely detected, although this is an active area of research. Two-dimensional system means two values are required. Two-dimensional system means two values are required to determine the position of an element. Next one is graviton. The graviton is the hypothetical quantum of gravity, an elementary particle that mediates the force of gravitational interaction. There is no complete quantum field theory of gravitons due to an outstanding mathematical problem with renormalization in general relativity. Renormalization is a collection of techniques in quantum field theory, the statistical mechanics of it, and the theory of self-similar geometric structures, and to treat infinites arising in calculating quantities by altering value of these quantities. In string theory, believed to be a consistent theory of quantum gravity, the graviton is a massless state of a fundamental string. If it will be exist, the graviton is expected to be massless because the gravitational force is a very long range and appears to propagate at the speed of light. Hadrons. Hadrons are defined as strongly interacting composite particles. Hedrons are either composite fermions, in which case they are called baryons, and it might be a composite bosons, in which case they are called mesons. Quark models, which is a classification scheme for hadrons in terms of their valence quarks, the quarks and anti-quark, which give rise to the quantum number of hadrons first proposed in 1964 independently by Moe Gelman and George Zwick, describe the known hadron as composed of valence quarks and antiquarks tightly bound by the color force, which is mediated by gluons. A sea of virtual quark antiquark pairs is also present in each hadron. Next subatomic particle is Hypron. A hypron is any baryon containing one or more strange quarks, but no charm, bottom, or top quark. This form of matter may exist in a stable form within the core of some neutron stars. Being baryons, all hyprons are fermions. That is, they have half-integer spin and obey Fermi-Dirac statistics. Hyprons all interact via the strong nuclear force, making them types of hadron. Its mean Hypron is the classification of hadron. They are composed of three light quarks, at least one of which is a strange quark, which makes them strange baryons. Ground state Hyprons decay weakly with non-conserved parity. Excited Hypron resonance typically decay by strong decays to the ground state Hyprons. Strangeness, which is a property of particles and will explain the quantum number describing the decay of particles in a short period of time. This property is conserved by the strong interactions. The ground state hyprons can't decay strongly, however, they do participate in strong interactions. Next is quasi-particles. Actually, quasi-particles are collectively excitation, or you can say they are closely related to each other when a microscopically complicated system is under discussion. These are effective particles that exist in many particle systems. These phenomena are actually, or you can say typically, called quasi-particles if they are related to fermions, and are called collective excitation if they are related to bosons. Although the precise distinction is not universally agreed upon, thus electron and electron holes, which are actually fermions, and they are also called quasi-particles, and phonons and plasmonons, which are bosons, are typically called collective excitation. Here I will tell you about some quasi-particles. These particles can be created and can be explored. One is anions. They are the generalization of fermions and bosons in two-dimensional systems like sheets of graphene. Next one is dislons, which are localized collective excitation of a crystal dislocation around the static displacement. Third one is excitons, which are bound states of an electron and a hole. Hopfions are topologically solitons, which are the 3D counterpart of the skyrmion. Magnons are coherent excitations of electron spins in a material. Phonons are vibrational modes in a crystal lattice. Plasmons are coherent excitations of a plasma. Plectrons are theoretical kind of particle discussed as a generalization of the braid statistics of the anion to more than the two dimensions. Polaritons are mixtures of photons with other quasi-particles. Polarons are moving charged quasi-particles that are surrounded by ions in a material. Skyrmions are a topological solution of the pion field used to model the lower energy properties of the nucleons, such as the axial vector current coupling and the mass. Braid statistics Braid statistics, which I have used this term in the slides. Braid statistics is a generalization of the spin statistics of boson and fermions. Next are the dark energy particles. These are unknown form of energy. Dark energy. Dark energy is an unknown form of energy that affects the universe on the largest scale. The first abbreviated evidence for its existence came from the measurements of supernova, which showed that universe doesn't expand at a constant rate. From this, a concept of dark matter arises. What is dark matter? It is that type of matter which we can't see. Actually, suppose that they are unstable. As we consider it a type of dark energy, then might be dark photons are present in it. We know any empty space or even vacuum will not be completely empty, or you can say it is not 100% empty. Might be it contains some massless virtual particles, or maybe some particles which are not discovered and we didn't know about them. Here I will discuss about two dark energy particles. Number one is chameleon. Chameleon particle is that whose effective mass is always in changing. Where density is low, its effective mass will increase, and where density is high, its effective mass will decrease. Where the effective mass is more, it exerts more force. Our solar system, which contain many particles. Due to these particles, relative density increases and their effective masses decreases. Due to this, exerted force becomes negligible. So we can't detect chameleon particle in solar system, or you can say it become impossible to detect them. But scientists believe that our intergalactic space is almost empty, so density is low here. Due to this, effective mass increases and exerting force becomes strong. According to the previous concept which I have discussed, so here it might be possible to detect the chameleon particles in the intergalactic space. In our solar system, it is difficult to identify these particles. That's why its identification is still a theory, but this theory is not rejected. Maybe in futures we will identify these particles. And the second one is epsilon particle. It is also the candidate for dark energy. Here are some other subatomic particles which are classified by speed. A baryon, or Its second name is Tritium, travels slower than the speed of light in a vacuum and has a non-zero real rest mass. A Luxon travels as fast as light in a vacuum and has no rest mass. A tachyon is a hypothetical particle that travels faster than the speed of light, so they would paradoxically experience time in reverse due to inversion of the theory of relativity and would violate the known laws of causality. A tachyon has an imaginary rest mass. Here are some other particles which are discovered and some are still discovering. Calorons, finite temperature generalization of instantons. Dyons are hypothetical particles with both electric and magnetic charges. Geons are electromagnetic or gravitational waves which are held together in a confined region by the gravitational attraction of their own field of energy. Goldstone bosons, which are massless excitation of a field that has been spontaneously broken. The pions are quasi-Goldstone bosons of the broken chiral isospin symmetry of quantum chromodynamics. And the next one is Goldstenoids, which are fermions produced by the spontaneous breaking of supersymmetry that are the supersymmetric counterpart of Goldstone bosons. Here are some more instantons, a field configuration which is a local minimum of the Euclidean action. Instantons are used in non-perturbative calculations of tunneling rates. Pomerons used to explain the elastic scattering of hadrons and the location of ridge poles in ridge theory. Actually, elastic scattering is a process in which kinetic energy of the particle is conserved in the center of mass, but its direction is modified. Spelrons are a field configuration which is a saddle point of the Euclidean action. Spelrons are used in non-perturbative calculations of non-tunneling rates. Second last is mini charged particles. They are hypothetical subatomic particles charged with a tiny fraction of the electron charge as their name indicate. Continuous spin particles are hypothetical massless particles related to the classification of the representation of the Poincare group. Its name also indicate. The working of these all subatomic particles are still in progress. Now I will tell you about Cern. Cern was founded in 1954. The Cern laboratory sits astride the Franco-Swiss border near Geneva. It was one of the Europe's first joint ventures and now has been the 25 member states. The instruments which are used at CERN are purpose-built particle accelerators and some detectors. Accelerators actually boost beams of particles to high energies before the beams are made to collide with each other or with stationary targets, and the detectors which observe and record the result of these collisions. Physicists and engineers at CERN use the world's largest and most complex scientific instruments to study the basic constituents of matter, fundamental particles. Subatomic particles are made to collide together at close to the speed of light. Scientists who work at CERN are trying to find out what the actually smallest building blocks of matter are. Normal matter is actually made of molecules, and these molecules themselves made from atoms. Inside the atoms there are electrons spinning around the nucleus. The nucleus itself is generally made of protons and neutrons, but even these are composite objects. Inside the protons and neutrons we find the quarks, but these appear to be indivisible just like the electrons. Quarks and electrons are some of the elementary particles we study at the CERN and in other laboratories, but physicists have found more of these elementary particles in various experiments, so many in fact that researchers needed to organize them just like Mendeleev did with his periodic table. Here are some big discoveries made at CERN. First one is God particle. On July on July 2012, two experiments at Cern Large Hadron Collider announced they had each observed a new particle in the mass region around 125 G electron volt. This particle is consistent with Higgs boson, but it will take further work to determine whether or not it is the Higgs boson predicted by the standard model. The Higgs boson, as proposed within the standard model, is the simplest manifestation of the Broad-Englert Higgs mechanism. Other types of Higgs bosons are predicted by some other theories that go beyond in the standard model. But in 2013, the Nobel Prize was awarded jointly to Francis Englert and Peter Higgs for the theoretical discovery of mechanism that contributes to our understanding of the origin of the mass of the subatomic particles, and which later was confirmed through the discovery of predicted fundamental particles by two experiments at CERN Large Hadron Collider. And the next one is W and Z bosons. In 1983, a decade after Cern scientists detected weak neutral currents, they discovered the W and Z bosons, elementary particles that mediate the weak force. The two W bosons, which is W plus and W minus, have the same mass, but they have opposite electrical charges, while the Z boson has no charge. Using a particle accelerator called the superproton synchrotron particle, physicists Carlo Rubbia and Simon van der Mee led a team that found proof of the bosons in experiments called UA1 and UA2. The two scientists were awarded the Nobel Prize in Physics next year. And the third one is light neutrinos. In 1989, Cern scientists determined the number of families of particles containing what are known as light neutrinos. Uncharged elementary particles with very little or no mass, neutrinos only rarely interact with other particles and thus are sometimes called ghost particles. The discovery of these light ghostly particles was made at the Large Electron Positron Collider using an instrument called the ELF detector. And the last one is antimatter. In 1928, British physicist Paul Dirac wrote down an equation that combined quantum theory and special relativity to describe the behavior of an electron moving at a relativistic speed. Dirac's equation could have two solutions, one for an electron with positive energy and other for an electron with negative energy. But classical physics dictated that the energy of a particle must always be a positive number. So Dirac interpreted the equation to mean that for every particle there exists a corresponding antiparticle, exactly matching the particle, but with opposite charge. For example, for the electron, there should be an anti-electron, identical in every way, but with a positive electric charge. But when matter and antimatter come in contact, they annihilate, disappearing in a flash of energy. Then Big Bang should have created equal amounts of matter and antimatter. So why in universe more matter is present than antimatter? Then this concept arises. Where is antimatter? By taking this concept, some scientists starting work on it. At Cern, scientists make antimatter to study in experiment. And in 1995, Cern scientists succeeded in creating a form of antimatter called antihydrogen, a negatively charged variant of hydrogen in the PS210 experiment at the low energy antiproton ring. However, the antimatter collided with matter and was annihilated before scientists could study it. In 2010, CERN's anti-hydrogen laser physics apparatus team created and corralled anti-hydrogen for about a sixth of a second. And in 2011, they maintained the antimatter for more than 15 minutes. Here is the references from where I have taken these data. That's all about my presentation. If there is any confusion or any query about the data which I have discussed here, you can ask me in comments. Thanks.